Hello, welcome back. So we are in week 7. We are in the third module now. This is the third video of week 7. So we'll continue our discussion on that problem which I was trying to solve in the previous video, towards the end of previous video. So let's what I've done in this is I have gone little few slides back so that we can just quickly recap the part of the problem that we have already solved, and then we'll go to the second part which we could not solve in the previous video. So let's get started. So this was the problem. We are looking at one biological treatment example where we have two waste stream. As I was telling, that if you are running a compost plant, it's not that you will only have one waste stream to deal with. You will have multiple waste stream to deal with. Many times to get the carbon nitrogen ratio, a good carbon nitrogen ratio, you may have to mix certain waste stream as well. So here we have two waste stream. One is the chicken manure, which is essentially the chicken waste which is coming from, say, any chicken processing facility where they are like processing the chicken and getting the meat out. So you will have all the feathers and all chicken poop and poops and all that things will be there. So that's one source is this, where you get this chicken manure around 10 tons per month. Moisture content is given, volatile solids and BVS. A range of BVS is given. So we thought we took the average of that value, if you remember from the previous module that we're talking about. The other is we have yard waste, which is essentially the garden waste. In Western world, they call it yard waste because of the front yard and backyard that most of those individual houses have. Here we call mostly garden waste or you can, yeah, it's mostly the garden waste. So it's there. It's the data has been given to us: 20 tons per month, moisture content 20%, volatile solids 85%, and then here we have been provided with lignin content. If you remember from the I think in the second week we were talking about that if you know the lignin content, you can estimate the BVS, because there is a relationship based on the research done earlier. We have a high relationship between BVS and LC content, where also LC is expressed in percent. So that's why your data has also been given in percent. So you have the 6%. So we'll use that information. So these are the two waste stream coming to a compost plant. Now the question that was given to us is if you have to find out how much compost will be produced. So the first question was there, that how much compost will be produced. Before we go to that question, as I was telling you, that if you know the lignin content, we can find out what is the BVS fraction, what is the biological volatile solid fraction. So lignin content was given us as 6% in the previous slide which you saw. We have 6% lignin content. So that 6% has been fed in here. So that and if you remember, I said in this equation that this LC has to be expressed in percent. So we just put 6, we don't put 0.06, and then you do this calculation on this math, and then you get your value as 0.662. So 66.2% is your BVS. So that's the data we know, we need to know for the calculation. So that's the BVS percent. So for both, if you look at both this particular this one and the previous one, if you look at the two waste streams, so it's so we have so for this slide we have the BVS fraction already. For this particular waste stream, we have this BVS fraction. We calculated that. We have this data, so we calculated that. And here we had the LC. From LC, we found out BVS, and that was 66.2%. So for both of them, we know the BVS content. And if you remember from that previous discussion earlier and also yesterday, that we have to look at this waste in terms of this particular pie chart. So here any waste that you have, especially organic waste, you have some water, you have some water present, and you have some water. So we have some water, we have some inorganic fraction, we have RVS, and then we have this BVS. So BVS is the fraction which reacts, which we talked about in the organic, especially in the biological treatment, whether you're talking about anaerobic digester or you're talking about compost, it's the BVS fraction which reacts. Not many times, not the 100% of the BVS reacts. You will have you will be given a treatment efficiency of, let's say, 90%, 95%. That means even out of 100 tons of BVS, 5 tons do not take part in the reaction. So that's what, but theoretically we are talking about the BVS fraction. So we need to know. So if you are trying to set up a compost plant, you need to know of the waste stream that is coming to your compost plant, what is the BVS content, because that's what going to react. Based on that BVS content, you need to come up with the design for your air injection system, when you have to supply the air, because you need to supply oxygen. So for both of the question, we already know the BVS percentages. That's why that part was important for us. So coming to the first question now, how many tons of dry compost produced per month? So in terms of dry compost that can be produced, so we have to look at, we had 10, if you look at the chicken manure, CM is short form for chicken manure here. So that's your chicken manure right there. So in terms of chicken manure, it was 10 tons and it was wet ton. That means moisture content is included in that. So if we find out in terms of the dry, 40% was the moisture content. So 60% is the dry content. So we can write down 1 minus 0.4 dry ton per wet ton. Then out of dry ton, 75 ton is VS. This VS and BVS, they are always expressed in terms of the dry. So you have 75% ton as a volatile solids. Out of volatile solid, we have 72% as the BVS. So we can do this math and then we can find out what is the BVS content, BVS, like how much tons of BVS out of 10 wet tons of the chicken manure. So this BVS is the content will get reacted, they will get converted to CO2 and they will get converted to water. So this is the amount which will actually react, and that yesterday, if you remember, we used the term destroyed. It's not really destroyed, it will get converted to other form. So it gets converted to other form, and that's what so it will not be there. The mass will get converted from solid to gas and liquid, and then we don't have that, we will not be looking at that particular fraction after that. So here they did the math, so we get 3.24 tons of chicken manure which will react in the system. So this is not the compost produced, but this is the amount, this is what is biodegradable and what will react. So compost will be total mass minus this. So that's what will be the compost. So the compost will be whatever is the total dry mass, out of 10 wet mass we can calculate what's the dry mass minus what is the BVS fraction which will react and go away. So you will have, you have 2.76 tons of dry compost which is produced from the chicken manure. Out of 10 tons per month, 2.7 tons of dry, it's the dry mass is what will be produced. So that's part of that. So that's for the chicken manure part. Then next is our yard waste. So similar things, if you can do it for yard waste. Here I have not done it that detailed step, because you should be able to do it by yourself. So we have 20 tons, 20% moisture, then we put the BBS and BS and BVS, all those things together, and we get 7 tons of dry yard waste compost which actually will come out of this. So you can do the math and you will find out the same number. So that's the amount of yard compost that will be produced from the yard waste. So this particular facility, it is taking both yard waste as well as the chicken manure. So if you add them up, it's 9.76 tons of dry compost. So out of 30 tons of raw waste coming into this facility, that's raw waste, it's including the moisture content, so including the water part. If you look at the dry compost, we'll have around 9.76, around 10 tons of dry compost. So 1/3 mass of dry compost that will be produced and from that particular facility. So that's one part of that, like how much this will be produced. The next thing is we will look at how much air we need to add. So we know that this compost will be produced. How much air we need to add, say for 1 year worth of compost. So just for our if you run this for the yearly run of the facility, how much air we need to supply. So we can do that calculation here as well. So when we say stabilization, we are talking about that yesterday and earlier as well, where 100% of the BVS, that's what the stabilization means. The 100% of the BVS is getting converted to CO2 and water. So that's the meaning of stabilization. So now the BVS has to get converted to CO2 and water. What does that mean? That means that we need to supply air, because as you know, composting is an oxidation process. We have to supply air for this for the reactions to take place. So we have to find out how much air will be required to add. because what is needed is oxygen. If you remember from that equation, which I will show you in few slides down the line as well, again, that it is the oxygen which will react, but we cannot just supply oxygen, we have supply air, and air is 21% oxygen. So we have 79% nitrogen and 21% oxygen. So it is only the oxygen that is participating, we know that part. So how do we determine? We can measure, we can do some lab test and measure how much oxygen is required, and we can do that too. But we can use the reaction from the previous slide. If it's 100%, and that reaction, if you remember, was essentially the reaction which is shown in this particular next slide, where you have this is the waste composition, and that's the BVS. This is the composition for the BVS fraction. So for the BVS fraction, if you know the equation of this, then you can plug all these A, B, C, D numbers in here, and you can find out, say, 1 mole of this will require how many moles of oxygen. So that's so for 1 mole of this, 1 mole of this BVS fraction of this waste, how many moles of oxygen is required, we can always find out using this equation, and then how much CO2 will be produced, how much water will be produced, those things can be calculated as well. So we can figure out the air, requirement for this equation, from this equation. So what we need for this equation? We need the formula for this. The unknown, number one thing we need is the formula. We need the formulae for this particular waste stream. And then, is it for the entire waste stream? No, it is for the BVS fraction. So we have to find out for the formula for the BVS fraction. Why? Because it is the BVS fraction of the waste which is going to react. Other fraction is not going to react. We have talked about that several times now. Other like inorganics and those plastics and other stuff will just go into the compost plant, and it will just carried with the compost process. It's not going to react in the equation. So it's only the biologically volatile solid, which is the BVS fraction, which will react. So we need to find out what is the formula for that BVS fraction. So let's try to do that for these two particular waste stream. So once we know the formula of the waste, I was telling you that once we know the formula of the waste, we can calculate how much oxygen is required. So here is one example, like how this is done. So here, if you have a simple organic say organic material C6H12O5, it's example for cellulose, and then if you do the same math as we were looking at in the previous, like take this as the A value, and this is our value for A, this is the value for B, and this is the value for C. And if you plug into those equation which was shown in the previous slide, we'll get this particular number. So what does it mean? It means that 1 mole of this will react with 6 mole of oxygen to produce this and stuff. So for our interest, what is the interest? We need to actually know what is the amount of oxygen that we need to supply, because once we know how much oxygen is required, we can calculate how much air we need to supply for that as well. So let's try to do that for these two particular waste stream. So we have to find out for the BVS content, we need it for the BVS content, what is the formula for the waste. So we need to get some information regarding the composition that's needed for that. Which part of the waste? Of course, for the BVS part. We have, like I think I have said that so many times now that you should not forget that, especially if you're working on compost or working on anaerobic digester, it is that biodegradable fraction which is going to matter. Other fraction doesn't matter. Other fraction just takes your space, and it doesn't. So that's why the source separation, when we talk about so much into the source separated organics, it's just the reason for that, because other things are just taking the space. It's not really adding any value, it's actually reducing the value of compost. So rather we don't have those, it's better for us. So if you look at the BVS fraction, the info is needed for that. So how we get that information? We can measure it, we can take the sample, you can do the CHONS analyzer. That's what is used, like you can do the CHONS analyzer, so you can get all those how much carbon, how much hydrogen, how much oxygen, and many labs have this kind of facility, including our lab here at IIT Kharagpur. So we can measure these things and we can find out, but if you have to do, as you know, the waste is a heterogeneous sample, you have to do multiple number of samples, so these are costly exercise too, but many times we have to do it, we don't have any other option. Just because it will be costly in the beginning, that doesn't mean that you go and design it for something which are not going to work later on. So we have to actually spend some money in the beginning as well to do a better design. So you measure it, so you get there will be some money required for that, but that's inevitable. We have to do that, especially if it's a waste which is kind of a newer kind of waste. There is no other data is available. Something which is well established, for example, yard waste, garden waste, flower waste, and there are certain kind of organic waste, typical agricultural waste. For that, a lot of research has been done from around the world. So, and the data is those kind of formulas are available in the literature. So, we can take the value from there as well. We can get either percentage values. These are the two ways you will see the values, either percentage wise, percentage carbon, percentage hydrogen, percentage oxygen, or you can get directly the formula as well. So, either of those can be available. So, based on that, you can always calculate the formula, and I will actually in this particular case, for to illustrate this point, for the one waste stream I am going to give you percentage wise data, and for the other waste stream we will use the formula data, so that we can see how to work our problem in either case, whether we have been given the percentage data or we have been given the formula. So, to do that, so for yard waste, simple yard waste, as I said many times, there are yard waste we have been using, this has been used for composting for so long now. So, there are we can get it from a reference from a compost book. There are a lot of compost books also available. So, you can yard waste typical formula is this. So, we can just use the formula directly, we do not have to actually do much. So, here we do not worry too much about the nitrogen, nitrogen is, we do not worry about the nitrogen contributing to air demand, but let us assume that it does contribute to the mass. So, we will not take nitrogen in terms of the air contribution. So, in this formula that is provided to us is the BVS fraction of the yard waste. So, this is for the BVS fraction of the yard waste. So, we know that formula, and then we can get that. So, somebody may have done the CHONS analyzer and then they got the number. So, that is based on that number we have come up with this formula. So, if we have this, that is one way of doing things. Other way of doing is, so if we have this, let's do this first. Then we have this formula. So, we have this A value. Sorry, you have this. So, you have the value for A, value for B. So, that is our A. I don't know. This is the value for B. We have value for C. And then we can plug those equation in here, A, B, C values, and we can get this much mole. So, 1 mole of this yard waste require these many moles of oxygen. This is what has been done here. So, we need 28.5 kg mole of oxygen per kg mole of the yard waste. So, that is it's again simple math, just following those steps. So, once you get those numbers. So, you plug in these values, you get this much moles of oxygen, and then how much moles of CO2 will be produced, how much moles of water will be produced. So, those things can be done. So, we got 28.5 kg mole of oxygen per kg mole of the yard waste BVS. So, now how do we got the oxygen. So, how we get how much air will be required? There are certain this is at the standard temperature and pressure conditions, 22.4 is standard meter cube of air is of a gas is there per kg mole. So, if you know the kg mole, for per kg mole, this is the amount of gas that is the volume of the gas. So, and the same thing for the gram mole, we can do that as well. So, 22.4 is standard meter cube per kg mole. So, that is the volume of air. That will be there for per kg mole. So, once we know the mole of oxygen, we can find out the mole of we can find out how much mole of the volume of that. So, here 28.5 kg mole of oxygen per kg mole of the BVS. So, for per kg mole of oxygen, the volume will be 22.4 meter cube. Now, for oxygen, so we can calculate this. So, if you do this calculation, you get 638 meter cube of oxygen per kg mole. So, here if you look at if you do this kg mole of oxygen and kg mole of oxygen will cross away, and then if you multiply to 28.5 times 22.4, which is coming from here, if you do this multiplication, you get this number 638 meter cube oxygen per kg mole. Now, we know 21 meter cube of oxygen per 100 meter cube of air. So, if we could do that, so this meter cube of oxygen and meter cube of oxygen will cross away. So, you have 638 times 100 meter cube per kg mole of this particular yard waste. So, these are all we are working per kg mole right now, and we had around we know the BVS fraction, which was some amount of ton, which we will see in a minute. So, this is next step is to convert per ton of BVS. So, this is the per kg mole of this particular material. So, this is what we got 3040 meter cube of air per kg mole that came from here. Once you do this math, 638 times 100 divided by 21, you get 3040 meter cube of air per kg mole. Now, 1 kg mole is how much kg, which will be the molecular weight. So, we need to find out the molecular weight of this particular yard waste compound. So, C27H38, so C is 12, carbon is 12, hydrogen is 1, oxygen is 16 and nitrogen is 14. So, if we take those numbers, we can calculate, we can take those numbers and then we get we can add them up. We get 632 is 27 times 12, 38 times 1, oxygen is 16 and 16 times 16, 1 times 14. So, you get 638 kg of this per kg mole. So, if you use this number now, so this much air per kg mole of this, 1 kg mole of this is 632 kg. So, now what you will get is this, in this case what you will, your kg mole and kg mole will cross away. So, what you will have is 3040 divided by 632, which is this number over here, 4.81 meter cube air per kg of your yard waste. Now, if you can convert it to per ton in 1000 kg per ton. So, from kg we can, so this kg and kg will go away and then we have tons now. So, we have this much meter cube. So, 4.81 multiplied by 1000. So, it is 4810, pretty simple, straightforward. So, this much meter cube of air per ton of yard waste BVS. So, this is per ton of yard waste BVS. So, we got this in terms of how much meter cube of air will be required. So, still we are on we are still working with yard waste. We still have to work on the chicken manure part. So, we are halfway through the question. So, we found out per ton how much air will be required for the yard waste. So, next is we have to do the chicken manure. So, as I said earlier, for just for the illustration sake, for chicken manure also the formula could be available in the book, for just to show you how to do the math when formula is not given, you only know the percentage carbon, percentage hydrogen, percentage oxygen. So, in that case how you approach the problem. So, in this case we have this data was available from before, we already looked at it. So, we have been given data in terms of percentage hydrogen, carbon, oxygen, nitrogen or sulfur and others. So, this data has been given to us. So, based on these data, we have to get the formula for chicken manure BVS fraction, and this data is for the BVS fraction. This data which is provided to us is for the BVS fraction. So, here let us assume that the components minus others. So, there was something others. So, we will just not include that in BVS. So, I assume that the components minus the others, because others could be something else. So, we have assumed that that's not part of BVS. So, so it's basically we have to make everything. See, if we take that 5% off, everything becomes with respect to those 95%. So, for others percentage wise numbers will go up. So, that has been done over here. So, we have increased the number accordingly. So, you have to, so the total has to add up to 100. So, based on that we get these are the percentages of carbon, hydrogen, nitrogen and oxygen. So, that is so here if you take 1 ton, so if you for the 1 ton how much carbon, how much hydrogen, how much oxygen, we can find out that, because we know what the percentage wise. So, for 1 ton what will be the individual elements. If you know the mass of the individual elements, what we can do, we can calculate how much moles are there, how much mole of this. So, 505 kg of carbon. So, carbon 12 kilogram carbon per kg mole. So, we can get all these kg moles individually. So, we can assuming that only carbon, hydrogen and oxygen. So, we can find out the formula in terms of Ca, Hb and Oc. So, here the carbon we got 42.1, hydrogen 67, 24.8. So, for 1 ton of BVS we can write down the formula as C42.1, H67 and oxygen 24.8. So, that is we get this formula for that part. So, once we have this formula, what we can do is we can again use the same equation as used earlier. So, we use the similar approach for yard waste. So, now the formula is this. So, for 1 ton of CMBVS, we can put how much oxygen will be required, we get this much moles. So, again here I will not, I will let you do the math details here. I will just show you the steps, and then you should be able to follow it if you have followed the yard waste nicely. So, you get to 46.5, and I encourage you to go back and do this math by yourself as well, just to cross check whether the numbers match, and that will help you to kind of if you miss some steps, it will help you to understand those steps. So, this much kg mole of oxygen per ton of chicken manure BVS, and then we can find out how much is the air required based on that, like this much per ton of chicken manure. Then that ideal gas law, assuming that the oxygen is behaving as an ideal, per kg mole is 22.4 meter cube. Then from oxygen to, so this much from oxygen to air. So, we can get, since we started with a ton, here we don't do the last step as we did for the yard waste. So, we are getting a 4955 meter cube of air per ton of chicken manure BVS. So, that is the data we have in terms of the air requirement. So, for both chicken manure as well as yard waste, we know per ton how much the air will be required. Now, the thing is that if you compare chicken manure and yard waste, they are pretty much similar. Little bit chicken manure requires a little bit more air than yard waste. It's probably has like more carbon, carbon and other things are there for reaction. So, these are the values for those two scenario, and then so the total air demand will be for chicken manure again this much meter cube of air per ton, and we know that 3.24 ton of chicken manure BVS was there per month. There are 12 months a year, so we can calculate how much for an year. So, we get 192 so as you can see here, this much per ton of BVS, this much tons of BVS. So, this tons and tons actually will go away. Then your month is 12 months per year. So, you come up with meter cube per year by year. So, this is the data you get for that. Similarly, for yard waste, you can do the math, and then you get this much amount of air that is required. So, for yard waste, we require more air because it is a more mass, isn't it? Here you have 10 tons, here you had 20 tons. So, that is also factored in there. So, to start with, and then there was so based on that we can calculate how much. So, total air required will be addition of these two. So, we have to add these two to get the total air required. So, that comes around 0.7 million meter cube of air per year. So, this much air is required in a year when you add them two. So, why we need this air numbered? So, again as I have been telling from the very beginning, for everything that you do, you should always try to understand why. So, here why we want this air number is because we want to convert, we want to buy those blowers. We have to know how much air we need to supply. So, we need to buy the blowers, and to buy the blowers we need how much is the air requirement. And if you look at any blowers or the pump data sheet, they typically give the value in terms of a standard cubic meter per minute or a standard cubic feet per minute. So, we have to convert this data for year, whatever is per year to per minute, how much data is required per minute to when we go and start shopping for those blowers or the pumps that we require for air addition. So, if you want to convert that, this much air per year, 1 year 365 days, as you can see over here, 1 year 365 days, 1 day 24 hours and 1 hour 60 minutes. So, converting this we need 1.33 standard cubic meter per minute. So, when we go out and try to buy the pump or the like the compressor, what we need to do it in this particular, we need this much. And here one assumption is there that the air requirement is uniform throughout the process, which may not be true. If you remember the other problem we did, we used this day 2 was the more critical. So, but here that assumption is there. If the assumption is not there, we can always factor those things in out. So, that is the air requirement. So, that is how we get the air, that is why we need to get the air calculation. Once you have that, you can design the compost plant. the compost design, there's the standard protocol is there how to design it, and of course if you need help, people like me is always available for help. So what other questions could you answer for this waste stream? How much water is produced? We can always find out how much water is produced. What is the moisture content of the final compost? We can do that. How much, if it's an anaerobic system, we can find out in the anaerobic decomposition, we can find out how much methane would be generated. We didn't do a math on that part. I would let you do the math. There could be math on that part in the exam. So don't complain later on that you didn't tell us earlier. So which is, but I am telling you right now that you can use the same concept and do the math using anaerobic digestion using this equation. So again, as you, if you know the amount of, if you know the formula for waste, you can also in this case you can also find out how much water we need to add, or how much methane will be produced, and how much CO2 will be produced. So these things you can find out as well, and how much ammonia will be produced. Those things can be done in similar problems can be solved, and which will talk about as like we haven't done the math here, but you can do those math. There could be some questions in the exam and quiz maybe. So other questions is that if the waste were mixed to achieve optimum carbon to nitrogen ratio, that also we didn't do any math here. We talked about that, how to get optimum CN ratio. That's again another very important concept, which is also like how to get the carbon nitrogen ratio. Carbon nitrogen ratio, it should be what we said around 25. So if I give you the carbon value, you should be able to find out nitrogen value. If I give you the nitrogen value, you should be able to find out the carbon value. So those things are there. Many times the chicken manure is high in arsenic. I think we talked about that. In some parts of the world, they feed rocks arson, which is basically an organic compound. But sometimes it doesn't stays ARSONE. It doesn't remain. It says AR. It doesn't stay within the chicken flesh, it goes out as a poop, but many times it does, since it's in the poop, it does show up in the chicken manure, and then if it's high in arsenic, that means the compost will have high arsenic content. So you can, if I give you the arsenic content of the raw material coming in, you should be able to find out how much arsenic will be there in the compost. So essentially, there's again a mass balance problem. We have done that similar problem very early in I think the week 2. Or early part of week 3, but this again for the chicken compost also you can do those kind of problems, and so try those like if you have any confusion what I'm talking about, ask us question on the discussion board. We'll be more than happy. So that's with this, let's close this particular video. So we have finished. This is the third video of the week 7. And with this, we have completed the biological treatment part. So in the next video, we'll go into the thermal treatment. So in the biological treatment, we focused on composting. We talked about the anaerobic digestion. We did not go into great technical detail because again, this course is in 12 weeks. We are trying to cover several aspects here. So we didn't, but I did tell you all the basic calculations that you need, how to go about design of the compost plant, how to approach design of an anaerobic digester plant. So all those basic homework that you need to do has been covered. Again, if you have any questions, feel free to contact us through the discussion board. For those detailed design, sometimes through the online course, it's a little bit difficult to do those detailed design kind of because what we will try maybe in later semesters, we'll try to just do a focused like 4 weeks or 6 weeks on anaerobic digestion or just on composting, just to go in more like a detailed step-by-step design of the plant. So with that, let's close this video. Again, thank you very much. Keep watching, and I hope you're enjoying this course.